Okay, the idea on the single machine infinite bus modeling is we want to give you some feel for what's going on with the frequency analysis and the eigenvalues in the system. And then the next topic I'm going to do is going to talk about modal analysis and frequency analysis, which we're getting into more and more at Power World. If you forgot what an eigenvalue is, that's okay. This isn't going to appeal to everyone, and I've taught this material. I mean, I've taught eigenvalues to our undergrads and modal analysis several times, and I tend to forget it. So don't feel bad if you just had it once and you've forgotten it. We all forget. But this can be a useful analysis tool if you're, again, having issues with the case and you're wondering what's going on. As I present this, I do want to say usually you don't use this to go looking for trouble. So I would not advise you to go out to this page just to see if there's trouble, because what we find is there are actually a lot of systems that have positive eigenvalues that we're not sure why they're coming up as positive, but they seem to be stable. So we'll get to that in just a second. But the idea on the single machine infinite bus eigenvalue analysis is we don't do a full modal analysis on our system by calculating this large A matrix. That's something that's known as small signal stability. Power World doesn't do that. And I think that's kind of falling out of favor a little bit as we get into more other analysis techniques. Rather, we do something where we look at each generator independently, and on the fly, we create what's called a two-bus equivalent for the generator. So it's like the generator is connected to the rest of the system through an equivalent impedance into an infinite bus. So you analyze just the local modes associated with that generator. Okay, and this can be helpful to some extent, but as I said, we don't go looking for trouble. So we're going to show you how to do this. The slide does say positive eigenvalues equals problems, but that's not necessarily true. Large negative eigenvalues can also indicate problems, so I'll talk about what that means, and we'll just kind of go through some examples here. Sometimes with exciters like the EST1 exciter, we can often get large negative eigenvalues. Large negative eigenvalues, these correspond to e to the lambda t, where lambda is the eigenvalue. If its real part is negative, that means it decays very quickly. If it's positive, it means it grows with time. Growing with time is not good. Decaying very quickly, we get into what we were talking about yesterday, a potential numerical instability. But most of these issues we have addressed by the subinterval integration that I talked about briefly yesterday. Okay, so this is most useful if you're having trouble with a model and you want to find out what's going on. So let's go ahead and open the case westexample.pwb, and we'll use that to go through this analysis. The slides are a little bit out of date because we did make a change in this, which I'll point out right now. So go ahead and open up that example. So you just have to open the PWB. You have an earlier case in there. Don't worry about it. Just ignore it. Okay, the change we made into the code was originally when you clicked on this, single machine infinite bus eigenvalues, originally when you clicked on it, we just let you go over there without validating the case. As we talked about last time, whenever you run a transient stability simulation, it automatically validates the case. We had allowed you to do that eigenvalue analysis without doing that, and we decided, this really doesn't make sense because they can't run the case without doing the validation. So why are we letting them do single machine infinite bus without doing it? So now you have to validate it. What I would like you to do before you click on that is change the time step to 0.25 cycles. Because without doing that, when you run the validation, you're going to get a ton of these time constants too small error. If you change that time step to 0.25, then if you click on single machine infinite bus eigenvalue analysis, it's not going to take you there. It's going to take you to validation because you've got some errors. These are the errors we talked about yesterday. Just run autocorrect on them, and you'll be fine. So usually you would be doing this on a case that's already been validated. Okay, so once you've validated it, then go to single machine infinite bus eigenvalues, which is right below it. Now all you have to do is click on the Run Single Machine Infinite Bus Eigenvalue Analysis, and it does, on the fly, it goes through, and for each generator in this system, it creates a 2-bus equivalent of that generator connected into an infinite bus, calculates its eigenvalues, and then stores them and goes on to the next one. The advantage of doing this is it's very fast. The disadvantage is you don't get inner area oscillations captured with this. So it's just a local screening tool. The most useful columns here are the max eigenvalue column and the min eigenvalue column. So it calculated all these values. What I tend to do is I sort on the max one. And what you'll find is there's a number of them that have positive eigenvalues. And we're working on tracking down what the issues associated with these. I think it has to do with what sort of input comes into the stabilizer. If you bring bus frequency into the stabilizer, there's some issues with that. But also you can have positive eigenvalues in a model that if that mode never gets excited, it's okay. That's why I say don't go looking for trouble. So don't go and say, wow, I got all these positive eigenvalues. This case must be horrible. That's not necessarily the situation. It's more if you're looking at, I've got a problem with a generator that you see in a run, that this generator is behaving strangely. Why might that be? That's where this becomes most helpful. Okay, if you click on the minimum eigenvalue, what you'll see is I sorted it on negative values. These very large negative values, like one of them has a value that is minus 2600, that's e to the minus 2600t. That's a mode that decays really quick. And those modes tend to be associated with these EXST1 exciters, very fast response on that exciter. Unless we did the sub-interval integration, we couldn't handle it. But because we do that, we can handle it. Okay, so you get a very fast responding exciter. What we're going to look at is just one example here, and that example is one of the generators that we talked about last time that has a very slow, unstable mode in it. We're going to flip forward to slide 12, cover the dialog here. So I'm on slide 12. Once you do this, you can get details on what it did by clicking on the row of interest. And if you right-click, it gives you 3 options that are key. The first option is you can show the single machine infinite bus dialog. That gives you a lot of details about what it just calculated, and we'll get there in just a second. The second option, which I use all the time, is save 2-bus equivalent. Save 2-bus equivalent saves that 2-bus equivalent in a PWB file that you can later analyze. This is super useful. If you've got a generator that's doing something weird in tracking down problems with a case, and I know a lot of you won't be doing that, but some of you will, if you save a 2-bus equivalent, you can isolate that generator and you can solve it really fast because it's a 2-bus case. You can change parameters around, look at what's going on. So I use that all the time. Show dialog just shows you the generator dialog, which you can then get and look at the parameters on the generator. What do we see when we look at these values? I'll go through this real fast, then we'll look at the dialog itself. Eigenvalues are telling how your system in that state is oscillating. And an eigenvalue is associated with a linearization about an equilibrium point. So we're at our equilibrium point for the transient stability run. You haven't done anything to it. This is telling you what's called a small signal stability of that generator. Small signal just means if you give the generator a little kick, how will it respond? The eigenvalues tell it how it will respond. The response has a frequency value and a real component. The frequency value is associated with the negative number. The real number tells you whether it's decaying with time or growing with time. So in a eigenvalue, you can have one that doesn't oscillate, it just has an exponential decay. You can also have an oscillatory exponential decay. If you've got no value here, no frequency or no imaginary number, it'll just exponentially decay or exponentially grow. If this value is non-zero, eigenvalues with non-zero imaginary components come in pairs. You've got a frequency associated with it. It's oscillating around. We'll show you that on the dialog, whether it has an imaginary part and hence a frequency or not. So quickly, large positive real values could be of concern. Large negative real values could be of concern. Very fast frequencies could be of concern. But usually they're not because of the subinterval integration. So we're going to look at one particular generator, and this is generator 50513. So if you go back to the SMIB eigenvalue display, and you page over or zoom, click over, I guess, to the left-hand side, sort on bus number, and then you go down to $50,513. Okay, it's 2325 is the number. Then right-click on that and show the SMIB dialog. This dialog has 3 pages associated with it. This is just general information on the generator, what its MVA base is, terminal voltage, stuff like that. The A matrix is the matrix, the code calculated to determine the eigenvalues. Usually you don't look at that, but if you want to look at it, usually it's not much help, except, yeah, usually it's not a lot of help. But that's the input A matrix. The one that's quite useful is the eigenvalue page, which is the 3rd page over. What you should do there is sort on the real part on that page. And this is one where it has a positive eigenvalue that's just a little bit positive, but this is a real instability. Okay, and This one is 0.0119, and it's positive. That means,
How are you sure that that is a real instability as opposed to one of these other things?
Right. That's a good question. That's not on the exam, John. The answer is I'm not. And I have worked on tracking down why we have these positive eigenvalues. They're associated with stabilizer inputs when there's a bus frequency input. And this A matrix is not calculated analytically, it's calculated numerically. And I think there's some issues with that. Okay, but in answer to why would you care then if you're not even sure, the why you would care would be, I've got a generator that's causing trouble or looking weird. Why is that? So I'm not looking for trouble. I'm not calculating all these values, but I've seen one. Maybe I'm doing a large system run like Gordon's doing, and I see something oscillating around. Is that numerical instability? Is that real instability? How do I know? So I go in here and I look and I see, is there a positive eigenvalue? If there is, I might want to investigate what's causing that. That's what we're doing. So in this case, this was an older WECC model, and it was one where there was actually a cause for this, and I'm going to show you how we can see the cause. So you look at these values. These are eigenvalues, damping ratio, the damping frequency in hertz. This is one where there's no oscillation. It's just, it would be decaying, or because it's positive, it's slowly growing. We then do an analysis to try to figure out what part of the model is causing this. This is known as participation factor analysis. We're looking and saying, what is the cause of this positive eigenvalue? And if you scroll across, you're looking for, these are participation saying, on this state, how is it participating in that positive mode? These are normalized values, so what you're really looking for is you're looking for something that's close to 1, and in this case, golly, governor KI is almost 1. There's something not right about the input to the KI. The KI is just a PI block on a governor, and if you don't know what that is, don't worry about it. It's an input on the governor. There's something wrong with this governor, potentially. So we go over to our model, and I can go over, let's see, I'm going to go out of this for a second, and what I'm going to do is I'm going to save this as a 2-bus equivalent. So I close the dialog, and I'm back on the SMIB page for generator 5052. I'm going to select right-click to get the local menu. I'm going to save 2-bus equivalent. So I'm going to save it. By default, it picks a name to save it. That name, by default, is just the generator underscore the number underscore the generator ID. Just go ahead and save that. Okay, this saves a little 2-bus case. So let's go ahead and open up that little 2-bus case. So File, Open Case, it should be in the same directory, and it should be right there, gen underscore 50513. Okay, you guys see that? 2-bus equivalent, open it up. Since there's no one line by default, it shows you the bus records. It's that same generator connected to an infinite bus. The code went through and calculated what the impedance of that line connecting this generator to the infinite bus should be. That's what we call the driving point impedance. Okay, and if you don't know what that is, you don't care. Okay, but it's very easy to calculate, and it's fast. let's look at the details on that generator. So I'm going to go over to the generator record here on the Model Explorer. So I just clicked on generators. Now I'm listing all the generators here. Right-click on that generator and do Show Dialog, and then go over to Stability, and you can see the models associated with that generator. Okay, the SMIB analysis told us that there was a problem with the governor. Okay, so I go and I say, I wonder if there's a problem with the governor. So I go over, and that's got a PID GOV model in it. Maybe you know what that is, maybe you don't. You can show block diagram. Most people aren't going to care, but that KI mode is this one right here. It's a PI controller. The input to that PI controller is coming right here with the speed, and then right there is coming from the top with our droop signal. Okay, so we've got a droop coming in there. That the details aren't particularly important here. But the droop gain there, the R value, that should always be positive. Okay. For whatever reason, in this model, it was negative. This R permanent value is minus 0.05. Okay. I'm sure this has been corrected. That will cause instability. So because we've got a little case here, we're going to run transient stability, and when it creates a two-bus equivalent, it automatically puts in a little fault for you, which is just fault the bus for a 20th of a second and then clear it. So go ahead and run that transient stability run, and you look at that response, and you think, oh, not a problem, that looks fine. Okay. Everybody get it fine? But run it for 1,000 seconds. So change the end time to be 1,000. You normally don't want to do this with a full WECC case. Okay. But this is a two-bus case, and it's going to run fast. So we'll run that. And there's the rotor angle going unstable at about 900 seconds. That generator has a slow, unstable mode in it that if you're running 30-second simulations, you're never going to see. So this error can, let's call it an error. I doubt if they really have a negative droop on their governor, but this could persist in a model for a long time because you're not going to see it. Somehow we found it, and I don't think we were looking for trouble, but sometimes these slowly unstable modes can manifest themselves in other ways. But that's one where here you do you're using this in a longer-term simulation, and suddenly stuff screws up at 900 seconds. There's nothing associated with that. That's not due to numerical instability. That's due to a actual mode. We've confirmed it with Eigenvalue Analysis. We saw it with the simulation, so it's there. The solution is just to fix the data, and let's say that really was just a typo. So we go in, and we're going to go change that generator's value. So I can go back to the single machine infinite bus eigenvalue analysis. I right-click on the line associated with that generator just to show its dialog. So I can get and see with the governor value there. Let's change that negative value 0.05 negative to 0.05 positive. Typical droop value is about 5%. So we're going to change it to 0.05 positive, click OK to save it. You can then run the SMIB. First of all, when you change parameters, you do have to click reinitialize. So that reinitializes the model because you've changed the parameter. Click reinitialize, then run SMIB analysis. And you should see your positive eigenvalue has now become a negative eigenvalue. Now you go back to simulation where we're running it for 1,000 seconds, and let's hope it works. So I'm going to run it for 1,000 seconds. And it's flat. You might notice there's a little bit of stuff going on there. Then it stayed flat. So when we do this sort of analysis, you know, I'm running at 1,000 seconds. There's no numerical problems with this. Okay, so I think the WECC case can be run long term if we get model issues addressed. I don't think there's anything in the code that is going to say errors accumulate or anything like that. I think we are okay with doing that, and we're working on doing those sorts of runs. Like just as today, maybe I'll show this tomorrow, we're putting in a proposal at University of Illinois to the Defense Threat Reduction Agency on looking at the impact of EMPs on the power grid. I'll talk a little bit about this tomorrow. But associated with that, we're running the WECC model for 100 seconds, and we are seeing problems pop up at 40 seconds. But we'll investigate to find out what's going on with that. Okay. But our idea is to run these things long term, and I think we can run them long term. So I think I covered everything in those slides. The takeaway on this is don't go looking for trouble, but if there is trouble, this can be helpful. And right before Gordon comes up, let me show you something that I find is a useful feature. When I run transient stability analysis, this is a bonus. There's a question of whether you want transient stability analysis form to live within the power world form. Okay, when we create forms, we can make them children. So this one can't be moved outside of the power world box. So if the power world box, the simulator box, becomes smaller, it's like stuck inside there. Okay. Some of you might like that. Jamie likes to keep stuff confined. When I do transient stability, I'm like, I want my transient stability form to be free. So I set mine free, and I got the option here. Now I can make it free. If you click on transient stability form, there's that little power world icon right there. When I'm doing transient stability, I think I'm doing transient stability. I want to put this on one monitor and then do other stuff on the other monitor. So I like mine to be free. So if you go and you click on the transient stability analysis form icon, free floating on top. The free floating lets it float outside of the power world window. The on top means it's on top of all your other junk. Okay, I like mine on top because I think I'm working on transient stability, so I want mine on top. So then I can move it. We only have one monitor here, but now it's like the main event, and you can stick it wherever you want. I like mine free. so we have that option. You don't like yours free?
I don't like it, no.
See, we have the free people and the confined people, so you can be whichever one you want. We give you choice to be free or confined.
Where did you access that from?
The way to make transient stability analysis free is there's a little Power World icon on the transient stability form, not this one on the form itself. Just left click on that, and it gives you a couple options. Free floating on top is what I like. I guess you can make it transparent too, but I don't think you'd want to do that. But it's just something. Jamie and I went back and forth on this because I'd be working on the form and I'd make it topmost so it'd be free, and then he'd put it back so it'd be less free, or it'd be confined as Caroline likes, and then I'd put it back free. So we finally decided to put an option in there. So
I get lost. Well, I guess if you put on top, but then it's fine. But you can free float simulator too. You can do this, I think, every window in simulator. You can do the same thing.
Yeah, because it's in the window. It's switched to free floating windows.
Yeah, but then that'll do, simulator as a whole, and then you can still do other individual windows like the transient one, like if you wanted to free float. I guess the only one I like, the message log, sometimes that's fun to float that one, but most everything else.
you have to be responsible with this,
Yeah.
With freedom comes responsibility. You can lose them and stuff like that, so you want to be responsible, or just keep them confined. That's okay.
I always want an upload bank.
Well, yeah. I mean, this is a really useful feature. I do it all the time because I'm like, Jamie, I'm working on transient stability. That's what I'm focused on. I don't care about this other junk. I want, and I'll put it on one monitor. I'll make it big because that's where I'm working.
So in the Windows tab, like Caroline was talking about, you can switch all windows to free or in a container. So my thought was, I was hoping that if I switched between those, it would reset everything. So in other words, if I had done it your way and I had transient as free, but then I went into the window and then said put all in container, it doesn't reset the transient to being container.
Transient's still free.
Right, because it's they're kind of.
What do you mean? Mine's now stuck.
No, but he's using the option that's on the.
Oh.
See, those are two separate things, because the first thing was the free floating simulator option, and then at some point it's like, okay, let's just do the individual free floating ones. So I think they're all implemented separately. Yeah.
I've seen Excel do things where if you open it to two windows and then you have a inside window way over here, but then you save it that way, open it up on one screen, you can't get your window that was over here back no matter what you do. It's until you open it up on two screens again. Is that a feature of what we're describing here?
There have been times where I've lost it. We've tried to address that. I mean, sometimes when you're moving between a multiple and a single, there can be issues, because when you are free, I mean, there's responsibility here. It's sort of saving where it is, and it can get off screen. Doesn't happen very often, but it can occur.
Okay.
Yeah, I've had people call too with, I think simulator opened up like real narrow. Was that you, Daniel?
No,
I think
but
it was
that happens.
It was a BPA person, I think. Yeah, and I don't know why that happened, but I think that was a free floating window issue. Like all squishy.
Yeah.
Technical term squishy.
That's why they don't like freedom. So. Just have to be responsible with it.